Hello, good to see you. Welcome to the last HPO seminar of 2017. I'm pleased to introduce Dr. Salvatore Federico as the speaker of the seminar today. Dr. Federico received his laureate in mechanical engineering in 2000 and his PhD in structural mechanics in 2004 from the University of Catania, Italy. Salvatore's academic career has been closely associated with Human Performance Lab. Before and during his PhD studies, he visited the HPL and worked with Dr. Walter Herzog several times. In 2005, he officially joined the University of Calgary as a postdoc fellow and worked in HPL for 3 years before securing a faculty positions in the Department of Mechanical and Manufacturing Engineering and the Center for Bioengineering Research and Education in 2008. Currently, Salvatore also has an adjunct position in kinesiology here at HPL. Dr. Federico has been active in the field of biomechanics. He has served as the secretary in the Canadian Society for Biomechanics from 2011 to 2016, and for the 2017-18 term, he is the CSB president. Congratulations, Salvatore. In his research, Dr. Federico is interested in the geometrical foundations of continuum mechanics and its applications to soft tissue biomechanics. His current research includes nonlinear elasticity, the theory of porous media, growth remodeling, damage, theory of defects, and uniformity. In biomechanics, his main interest is in the establishment of constitutive models of soft tissues based on the microstructural features of the tissue. Recently, Salvatore started learning skating, and he is proud to have completed his first 3-month course unhurt. Despite his excellence in sports and academia, Salvatore is quite bothered by his constant difficulties in distinguishing left and right. If it makes you feel better, Salvatore, studies have shown that people with left-right confusion has quicker judgment on bilateral symmetry. Also, the great German physicist Helmholtz had the same problem. Salvatore divides history into before and after he lost his hair. In his seminar about his career today, we look forward to listening to both halves of his history in his talk, Biomechanicist by Chance, an adventure in continuum biomechanics. Please, Salvatore.
Thanks, Ekwan. Okay, good afternoon, everyone. So today I'll talk a little bit about what happened to me and why I'm doing biomechanics for a living. You know this. You know this word. Continuum means that my study of biomechanics is based on continuum mechanics. Continuum mechanics is the study of matter at a scale at which we don't care about the presence of atoms. We pretend that everything is a continuum so that we can do all the fancy things, derivatives, integrals, like we do in calculus, right? So the reason why by chance is that really I came here to Calgary completely by chance. For me, Calgary was the place of the Olympics, of the Winter Olympics of '88. I remember myself in the big bed with my mother and my brother. We were watching the figure skating, and that was it. I didn't know anything else about Calgary. So in ISB 99, what happened was that Walter organized ISBN 99, and also with Benno, they organized 2 satellite symposia. One was in Banff about gait analysis, organized by Benno, and one was in Kenmore about muscle, of course, and it was organized by Walter. Now, the professor in Catania, Guido La Rosa, that became my doctoral supervisor and my thesis supervisor and my doctoral supervisor the following year, he had to go to one of these symposia, precisely Benno's symposium on gait analysis, and went to the wrong one. And so he met Walter Herzog. And that's why we have this connection. And then the following year, he and Walter agreed to have me here in Calgary to do my laurea, my undergraduate thesis. So, well, of course, needless to say, now he's not here, so I can say all the fanciest things without looking flattering. I owe a lot to Walter. I learned an enormous amount of things: how to be a scientist, how to write papers, how to write grants, how to be a supervisor, how to be a team leader. I can't express my gratitude to Walter. So in 2000, 2001, 2, and 3, I was a visiting student for a few months a year. This was due for my laureate thesis. This was during my PhD. And then in 2005, I started my postdoc here in Calgary, and thinking to stay for a couple of years. And in fact, it's 2017. I'm still stuck here, probably forever. I don't think I'm going to move at this point. But we all, for example, Walter also had this idea to come here for a couple of years. Still here. Marcelo Epstein also came here for a couple of years. Still here. So it's a disease about Calgary. So to give a little bit of history, I started my laurea in civil engineering at the University of Messina. This is my hometown. And then I wanted to do mechanical engineering. So I said, well, mechanical engineering, I'll go to Torino, Polytechnic of Torino, no kidding. So I stayed 1 year in Torino. And then everything went very well, except I felt it was very, very far from home. Right? You don't foresee your future, right? So I felt it was very far from home. So I went back to Sicily, went to Catania, where there was mechanical engineering. So I completed my degree in mechanical engineering. And so Catania was a lot of fun. There's the volcano, there's the Etna, earthquakes, it's beautiful. And the Etna, the rafts, it's fantastic. So I did my doctorate in structural mechanics, as Kwan mentioned before, and then I came to Calgary between the two and during the doctorate to work with Walter. And then I did my postdoctoral fellowship also with Walter, and then I became a faculty member in 2008. So my research is in the foundations of continuum mechanics, and a lot of the way in which I look at continuum mechanics today is inspired by Marcelo. That is my other big lighthouse in my scientific life. And I've been working on the geometrical theory, so I studied a lot of differential geometry in the past years. And with my students now, we're working a lot on inhomogeneity theory, following Marcelo's works. Then I've been always working in solid mechanics, elasticity, porous media, composite materials, and in biomechanics. Of course, I've been working on this a lot with Walter. I started with joint contact mechanics, then cartilage and chondrocyte mechanics, microstructural constitutive modeling, and growth remodeling. And growth remodeling is a topic I share with Alfio Grillo, and I will tell you something about Alfio a little bit. Some of you know him. So the motivation for my interest in biomechanics was, well, this mistake that my supervisor made when he came to Canada the first time, and also articular cartilage. So Walter proposed two topics and said, well, would you like to do cartilage or muscle? I looked at them and I said, well, this looks more like solid mechanics. Let's do cartilage. Totally by chance. You can see it's completely random. So cartilage, you know better than I, is the tissue that covers the end of the bones in the arthroidal joints. And it does all the things, transmits a load, redistributed stress. It's a lot better than having bone-to-bone contact, which happens to osteoarthritic people, and provides a very low friction contact. It is made of a matrix, essentially proteoglycans. Then there is a fluid, there's essentially water with a lot of ions. And there are the collagen fibers, which you don't see in these micrographs, so I made just a drawing. This is courtesy of N.J. Clark, that a lot of you remember. And that's a chondrocyte, it's a cartilage cell. So we typically divide cartilage in three zones. So we have the superficial zone, the fibers are parallel to the surface, the cells are flat. Middle zone, everything is isotropic, which in dollars means that the cells are spherical and the fibers are random. And in the deep zone, everything is aligned, the cells are all aligned and they are elongated, and the fibers are aligned in the direction of the depth. So you see it has a very complex structure, and there is more to it. Of course, we have to look at the chondrocytes if you want to see how cartilage works from the biological point of view, because they do all the job in synthesizing matrix macromolecules. And the other structural molecules that are important are the proteoglycans and the collagen fibers. So the proteoglycans are these bristle brushes. You know, in Sicily we have this expression, to do the bottles. To do the bottles, those of you who have been my students know this expression. So to do the bottles means to clean the bottles before you do the tomato sauce that you store for the whole year. Now you do this in August typically. So that reminds me a lot of the bristle brushes they use for the bottles. So these bristle brushes are actually electrically charged, and we will see in a moment what they do. And then the collagen fibers the collagen fibers are a sort of, from my point of view as a mechanical engineer, they are a structural reinforcement. And in fact, what happens that the collagen fibers retain the proteoglycans in place, so they are not washed out by the fluid. And the proteoglycan matrix holds the fluid. By virtue of its electrical charge, they are able to hold a lot of fluid, up to 50 times its weight. A proteoglycan molecule can retain 50 times its weight in water in vitro. In the tissue is different, but in vitro it can be 50 times. And the fluid does a lot of things. For example, from the biological point of view, nutrient transport. There are no blood vessels, there are no other, there is no lymphatic system. Everything happens through diffusion, advection, convection, and all these fancy things that we are studying with Cotaiba, for example. So as far as the electric charges go, the collagen fibers are neutral, the proteoglycans are negative, and the interstitial fluid is positive because all the ions have gone in the fluid and to balance to make it neutral. So because of the self-interaction between proteoglycan and the interaction with the fluid, the tissue is able to sustain compression. Whereas all the other fancy things, so shear and tension, go to the collagen fibers. Okay? So as far as the solid-fluid interaction goes, and that's another topic that is very dear to me, the collagen fibers apparently deviate flow. There's a thing that has been neglected for a long time, and now everybody uses this thing. And the proteoglycan matrix does the bulk of the flow resistance because the proteoglycan mesh is so dense that the permeability of cartilage is very, very low. It's very difficult for water to flow through the articular cartilage. So there are a lot of tests you can do on cartilage. One is the classical confined compression. You have a rigid chamber. And rigid means, of course, it's metal, which is a lot, even if it's plexiglass, it's a lot stiffer than the tissue. So mechanically, that's pretty much rigid. And then you have a porous piston. You impose a displacement or a force and see what happens. So the fluid can go only out from here, right? Because the other walls are sealed. And so with this, you can study the inhomogeneity. So for example, if you use the cells as markers, like in the 80s, you can track the position of the markers. And in these laboratories, I don't have to explain you what happens with the markers. So you can measure deformations by looking at the markers. If you want to do something fancier, then you give a call to Nquan, and Nquan will create a mesh with this laser. And the confocal microscope will make a mesh, and you can see the deformation of the mesh. And then it will give it to Scott, and Scott will do some Wurzus things and show the deformations. Science fiction, beautiful things. But anyway, what happens is that the tissue is very inhomogeneous, as you can see. This is what happens in this direction. The tissue is also anisotropic, which means that the properties depend on direction. So I'm looking at this direction only. Look at the stiffness. Very low in the surface, very high in the bottom here, in the deep zone. And look at the permeability. Starts low, then increases. Oh my God, and then it decreases again. This oh my God is very interesting. It's one of the things that I like to do more during my postdoc. I will tell you about that. So it's very inhomogeneous anyways. And it's also nonlinear. Look at this. This is a stress strain curve in confined compression. It's been done by Holmes and Mao, 1990. So can you see? Of course, small deformations is about linear, and then boom. It's very nonlinear. Same thing with the permeability. Permeability is not constant. You compress the tissue, the pores become smaller, the permeability becomes smaller. So you can also do unconfined compression. These are two of the many tests you can do. There's indentation, other things, but let's focus on these two. So you can measure properties in different directions. And so you can look at the tissue anisotropy. No? So what happens in one direction is different from what happens in another direction. It's not like in the basic course of solid mechanics that you take in second year. Okay? Or in third year if you're in kinesiology, I believe. So, important features of the tissue: it's multiphasic, solid fluid ions. It has a microstructure. We have to take account of the cells, of the proteoglycans, of the collagen fibers. The properties depend on direction. So it's anisotropic. It's inhomogeneous. The properties depend on location. And it's nonlinear. So it undergoes large deformation, and things become all nonlinear. All the classical mass spring type of analogy doesn't hold anymore. Okay, so I will show you a little bit. I'll talk a little bit about what I've done in articular cartilage mechanics through these years, and so we'll talk about all these things, and we start with contact mechanics. This is actually a plot from my thesis, from a laureate thesis that I did that summer of 2000, when I came the first time, and this was a simple study on looking at, for example, normal, early, and late osteoarthritis, how the pressure distribution changes. Late osteoarthritis, just by tweaking the properties of the tissue, we know that in an osteoarthritic tissue, the permeability is higher, for example, it can double. So everything changes in the stress distribution in the joint. And I also studied boundary conditions problems. So is it better to model cartilage with the surface completely sealed, partially permeable, completely permeable? So I did this type of study. And then on contact mechanics, many of you know this fellow, that's Sang-Yu Han, just known as Han, and everybody in his family calls him Seung-Hon, which has nothing to do with Sang-Yu, but anyway, that's what it is. I was the only one, so it was just myself and all the Korean students that would call him Seung-Hon. Everybody else would call him Han because he would introduce himself by Han. And so we did this study. This was his master thesis on joint misalignment, and just showing the contact pressures when the contact pressure in patella and femur of that's a cat. It's a scan taken from a cat, and you can see the stress distribution is completely different. The center of pressure moves through the joint, so zones of the joint that are very loaded become less loaded, and zones of the joint that are almost no loaded, very little load, become heavily loaded, and so everything gets disrupted, and then that justifies why we get osteoarthritis in these cases. So then I started to work during my PhD, and then also my postdoc. I started to work on these microstructural models. And so microstructural is the antithetic of phenomenological. Phenomenological is a black box. I take a model has some parameters, I fit the parameters, I fit some set of experimental curves. Beautiful, works in a lot of occasions. Give me, if I can paraphrase my countryman Archimedes, give me a large enough number of parameters, and I will fit you the world. So I can, but then I don't get information on who is doing what. So I like to work microstructurally, and so I like to look at the role of each structural element, at the spatial organization of the structural elements, which explains why the tissue is anisotropic, why the tissue is inhomogeneous. And that's why I like to work. I prefer microstructural models to phenomenological models. Nothing wrong with phenomenological models, but there are just things the phenomenological model cannot explain. So this is a drawing I did, under my directions, Jorge, some of you remember, did for me many years ago. So that for me, the yellow thing is a genetic fiber that passes by a point. I look at the tangent to the fiber, I take the direction of the fiber, I have a probability distribution to find the fiber in that direction, and then I homogenize things. That's called the homogenization procedure. And I do an angular integration over all the possible directions, and I get an average of the properties at that point, given the distribution of probability to find the fiber in a certain direction. So with that, I was able, with a model that I call TITH, transversal isotropic, transversally homogeneous. This is a terminology I don't use anymore, so forget about it. But anyway, this model, this is the curve that I showed you before, the experimental curve made by Shinagel in 1997. And the yellow one is my curve. And so you say, hey, look, it's fantastic. No, that's wrong, because the model had the wrong premises. Unfortunately, it was a linear model, it was a linear elastic model. And I was not accounting for the fact that the collagen fibers behave very differently in tension and in compression. I remember I had a fight with Leping, not a fight, a discussion with Leping in a seminar many years ago. And so, that's the problem. No, this is very stiff. No, it's not very stiff. Okay. So we have to change a way of doing things. And while this is this was a nice way to look at things, we have to change completely mathematical apparatus. And I will show you what happens. But in the meanwhile, we use this model, always with Senghun. We use this model and to create micro models for cell deformation. So this was the first study that we did, microstructure on the cell. I had another paper earlier on cell, how to find the properties of the cell given the properties of the tissue and some weird mathematical things. But this was done with essentially finite elements using the model that I showed you before. And after that, then Enkwan worked a lot on cells using partially models that we developed in this period. The nonlinear ones, though. Okay, so then in 2008 we published this work. This was towards the end of my postdoc, beginning of my professor position. And we took the average, so for the linear model, we take the average of the, let's say, the elastic constants. So more precisely, I should say the elasticity tensor. Whereas in this case, we take the energy of the elastic energy. Okay? So that thing that I call elasticity tensor is the elastic energy for a linear material, practically describes entirely the elastic energy. For a nonlinear material, we have to integrate an energy. And so we also impose that the fibers can only bear load when they are extended, which was the problem of the linear model. They couldn't make the distinction. Okay, so then a couple of years later, with Christian Gasser from Stockholm, we made the finite element implementation of this, and now this works and has been used successfully in a lot of other works. And Quan is further developing this to study cell compression with this new model that is better than the other models. And so this is just an example. I don't want to show you the math because the math looks ugly. I mean, it looks beautiful to me, but probably you find it ugly. And this was just an example that we did, layer of cartilage, calculated stresses, just to show that the model was stable and would converge. So then after I was modeling the elastic properties, then I had a seminar here in the lab, and I had a question. The question was, having modeled the effect of the fibers on cartilage elasticity, have you thought about the possible effects on fluid flow? And I always like to acknowledge Vincent for having asked me this question, that it opened a whole new field of research to me. And then, in fact, we still use these models that we developed in that period. So what I do for permeability, I imagine that this is my cartilage. That's a potato. I know it looks like a potato, but I'm a continuum mechanics guy. We talk in terms of potatoes. Now we say the reference potato, the current potato. So I have my potato that is made of a porous matrix reinforced by fibers. Okay, so what I have, if I decompose the thing, because that's what we do, we decompose things in some way. So I have a set of micropores, or microscale pores, and then I have a mesoscopic scale of pores that are made by the interstices between the fibers. No, so this will be like a bowl of spaghetti that is boiling, or without, maybe not boiling, and this will be something denser than that. Will be replace the water in which the spaghetti are boiling with a sponge, and so the spaghetti will be the reinforcing fibers. No? That was my idea. So working with this, we started by looking at a little element of volume. It's called the REV, representative element of volume. So we look at one direction, we impose a pressure gradient, do the calculations, see what happens, and then use the probability distribution that describes the fibers and obtain the permeability of the tissue. So this is the graph I showed you before with the experiments by Marudas done in '68. This is a little 2-page Nature paper about cartilage, and she noticed everybody was thinking the permeability has to go this way because the product ligand density is known to decrease. They are very dense in the bottom, and they are less dense in the superficial zone, and it's about linear. So you respect there are less product ligands, the density of product ligands decreases linearly, the probability maybe increases more or less linearly. Okay, yeah, maybe more or less linearly, more or less, but then boom. And this, as Marudas and Boulot inferred, probably is because they wanted to measure the permeability in this direction, but the fibers here were creating a further obstacle to fluid flow. right? And so I said, that's beautiful. Let's use the model and see what happens. I couldn't believe it. And so, yes, it worked. And so we said, probably this works. And we developed it more. So now we have a comprehensive nonlinear model that accounts for the compaction limit. Compaction limit means when all the water goes out. Now, cartilage compresses because the water can go in and out. But if you hypothetically take out all the water, then the solid phase remembers that, oh, I'm incompressible. I'm not going to compress anymore. And so there is a compaction limit in this model. We have the statistical fiber orientation. We have the nonlinear elasticity from the previous model of 2008, and the effect of large deformations on permeability. And this has been done with Alfio Grillo. And then with one of my students, we did, Alexander Tomic, we did this application to articular cartilage. We used this model and implemented large deformation in unconfined compression. Just to give an example, this is just a plot of the radial flux. You see there's more flux here. There is zero flux, of course, on the axis. That's an axisymmetric piece of cartilage. Okay? Just to show that the model was converging, was working properly, was giving physically meaningful results. So, in summary, with this whole part of research, now we have this general large deformation model that is integrated with elasticity and the permeability. And we can account for strain-dependent matrix permeability models. We use the Holmes-Mao model. We can use experimentally determined probability distributions. We have used that by Mollenhauer. There is this beautiful paper in which they do X-ray diffraction of the cartilage, and they find a big peak in the deep zone. There is a peak like this, very small variance, so the fibers are pretty much oriented this way. In the middle zone, they get just white noise, which means random distribution. And in the superficial zone, they get boom. They get another peak here. So the fibers are parallel to the surface. Okay? And we have a full finite element implementation. We have done it with, now we use FEBio all the time. Scott here is the Pope of FEBio. Okay, so current work that is being done. Amir, my student Amir, that is now in Iran eating a lot of food from his mother. He's working on tissue damage model. He has a model for damage mechanics of collagen fibers. Now we want to extend that to damage of sheets of fibers, because in some occasions it has been argued that the collagen fibers in cartilage may be arranged in sheets, not just in single fibers. And Kotaiba, as I mentioned, is working on the connection between permeability and diffusivity of chemicals in articular cartilage. And Mosen, that you should remember, he was here until last year. And Mosen has worked on the improvement of the permeability model. We are still, we published one paper, now we are working on another one, and hopefully we'll submit it soon. And as I mentioned, Enquan is doing, in his spare time, is doing this, when I have time and he has time, we sit together and we work on this improvement on the cell model. So now, I would like to talk about one last topic, and this is a topic inspired by Marcelo. Marcelo, in one of my visits in Calgary, so first of all, he has this beautiful paper with Professor Mogen that unfortunately passed away last year. It's a big loss for the world of continuum mechanics. Marcelo and Gerard have worked together for a long time. They were born a few hours away, one in France and one in Argentina. And Marcelo was born on the 3rd of December, and Mogen was born on the 2nd of December. So they've been working together for a long time, and they did this beautiful paper on the International Journal of Plasticity on growth and remodeling. This has now a few hundreds of citations, which for a paper in continuum mechanics is a lot. I know in biomechanics, a few hundred is not a lot, but in continuum mechanics is a lot. Particularly if you open the paper and you try to read it, there's not too many people that can read the paper. So Marcelo practically proposed me to work on growth and remodeling back in about 2002. And at that time I felt, I'm not sure I can do this, but I know someone that can. And this person was Alfio Grillo. Alfio Grillo is my alter ego. Alter ego meaning that when I had hair, we looked, and he was younger, and I was also younger, because in fact I had hair. We looked almost brothers. A lot of people thought we were brothers because we looked a lot the same. And we use the same notation. My students will realize that from the little bit of blackboard you see there, it's exactly the same notation. We write in the same way. We work on the same things. We have, except for the hair, we have a lot of the same problems. And our students become friends just by this hereditary process. And Alfio and I have been working together forever. And this is when I said, Alfio, I don't think I can do this, but I think you can. And in fact, he did. And he started this stream of research for us in growth and remodeling. And we've been doing a lot of things in this. And I will show you one result today. But before I do that, I also want to tell you that also Alfio growth and remodels. And in fact, he has changed a little bit too. Now you can have, in Continuum Mechanics, you have reference configuration, you have current configuration. There is a map that does this, and so there has been a map that changed Alfio a little bit. So this was Alfio when he finished his PhD, I think. This is Alfio today, when he's a professor at the Polytechnic of Torino. And not that I don't remodel, I also remodel. So this was me in front of 222 over there. There was the office assigned to me that summer, together with Rashid. Those of you that have been here for longer will remember Rashid. And yeah, that was me. You can see I had hair. No, when people say, oh, no, I don't believe you about hair. No, I did. And so, yes, there was a, yeah, that's why I shaved today, so I can show you actually that's me. Okay, good. So, I shave very occasionally. So, yes, and and this particular result on growth and remodeling I'm going to talk about is on cartilage and was inspired by Professor Giaguinta. Professor Giaguinta was our professor of quantum mechanics in Catania. Believe it or not, we did, both Alfio and I took quantum mechanics. We did quantum mechanics, a few courses. We were in mechanical, but with the specialization in materials. And so we did all the fancy quantum mechanics, solid state physics, polymer chemistry, all the fancy courses. And I'm glad I did those. And Professor Giaguinta was a very eclectic professor. You can see he's on his desk putting painting. He had a big passion for art and for a lot of things. And this picture was taken by Gian Domenico. He was another student of Professor Giaguinta. And he had this idea, Professor Giaguinta had this idea, and he had an intuition. He told me, I showed him the distribution of fibers in cartilage, and he said, well, you have an angle here like this in the deep zone, superficial zone, the angle is like that. Why don't you use a Ginzburg-Landau or a Allen-Kahn energy? An Allen-Kahn energy or Ginzburg-Landau energy is an energy that is not convex. Now, if you look at the energy of a spring and mass, it's like this. It's a parabola. The parabola is the convex curve. No, there is a minimum here. You know that there is a minimum, no displacement, no force. You put the displacement, you pull your spring a little bit, the energy will go up, no, quadratically, and the force will be linear if it's a linear spring, right? So a Ginzburg-Landau, instead, a Ginzburg-Landau has two minima. So this is what Professor Giaguinta would call either a dromedary or an upside down camel, depending on the frame of reference, okay? So he said, you have to look into the dromedary, you have to look into the dromedary. Many years later, we did finally do it. And we actually reproduced what happens after remodeling, what happens to cartilage in healthy tissue. You see, there is a definite superficial zone, you see? This is the same color code. This is an experimental study that we got from a paper in osteoarthritis and cartilage. And can you see? The model does actually reproduce the same distribution you see. And this is just by giving the initial conditions so the boundary conditions of the fibers have to be like this in the deep zone. And there is no other way really, because the fibers in the deep zone are actually anchoring the tissue to the bone. So they have to be that way. They have to be that way. And then the other boundary condition is in the superficial zone, they have to be like this. And they have to close the tissue somehow, so they have to be that way. So just imposing the boundary conditions, we got the same distribution. This is the same thing that happened in osteoarthritic tissue. Can you see how small the superficial zone becomes? Because the fibers lose organization in osteoarthritic tissue. They are not nicely organized in the superficial zone. There is this red, here you see almost none, but there is this red. Red is 90 degrees, like this, is orientation. You see this red because it's the boundary condition. It has to be, even a very, very, very small depth, it has to be 90 degrees because of the boundary condition. Okay, so this was the result I wanted to show you with growth and remodeling. The way this has been done takes a little bit of time and a few hundred kilos of mathematics. But so if you look at what we have today we have these elasticity permeability models that are widely used. So it's not only our group that uses these models. Now, a lot of other people are using similar models. Maybe they make their own permeability model, but they are essentially acknowledging finally that the collagen fibers have a role in cartilage permeability. And in fact, until that paper that I showed you, everybody was assuming, no, it's just a proteoglycan. Who cares about the fibers? No, sorry. Otherwise, that result from Marudas that was published 40 years before couldn't have been explained. And so we have this growth remodeling model that captures the fiber arrangement. So given the initial condition, the boundary conditions, vertical here, horizontal on the top, the fibers have to be in that way. And that's with an Allan-Kahn or Ginzburg-Landau energy, like Professor Jaguinta was suggesting. So for the future, we want to study more the interactions between material properties and osteoarthritis. So what happens when the tissue is osteoarthritic? Is it going to remodel in a different way? Of course, yes. And how? And quantify that. And so we would like to go a little bit more from basic science. This is very basic science, but we want to go closer to clinical applications. So an idea would be, for example, with the work that Kotaiba is doing, we would like to see, we know that the permeability of cartilage changes with osteoarthritis. What if we can correlate precisely the permeability with the diffusivity? Well, the diffusivity can be measured in a non-invasive way, MRI. That's almost all they do with MRI. They do diffusion tensor analysis. And so if you can quantify that, you can probably have a hint whether the person has osteoarthritis or not. That would be our dream. But we need to find the correlation properly. Okay? So the hope is that this research is useful for going step by step from basic to applied. Someone has to do the basic research. It's like being the president of the Canadian Society for Biomechanics. It's like shoveling snow. Someone has to do it. Okay? So I'd like to acknowledge Christian, in alphabetical order, Christian Gasser from the KTH. We've been working together. We are now working together also with Amir with this damage model. Professor Jaguinta from Catania. Alfio from Catania, but now he's in Torino. He's been in Torino for a while. Sangyu or Sanghoon or Han, that is now at the Korea Institute of Technology in Cheonan. It's close to Seoul. And Walter, of course, and Professor La Rosa that mistook conference and opened this door in my life, and John Wu with whom I've been working in the past years, sometimes at the beginning of my career, and recently we published another paper together. And Marcelo, of course. Sorry, I forgot to mention Marcelo here, but Marcelo is, of course, my whenever I always tell my students in Continuum Mechanics, whenever there is something I don't know, I call Marcelo, pretty much. So, and I would like, in the end, to dedicate this talk to Professor Jaguinta. This was a couple of weeks before he passed away. Last year, we went to visit him. This is Leo. This is Luca. Luca was very chubby. And it was just 2 weeks before. And so before I start to cry, I'd like to remind you that we have the Congress of the Canadian Society for Biomechanics in Halifax. It's going to be a lot of fun. The website is up, and we will do a lot of other fantastic things like opening the abstracts, the call for abstracts, and hope to see a lot of you there. Thanks a lot for your attention.
Salvatore. Great talk. Now, the floor is open for questions.
In the remodeling study, what are the cells wishing to do? So they're following some recipe for how they're supposed to be.
They are being ignored. They are being ignored. We are imposing remodeling. So the way this is done mathematically is with the so-called two-layer kinematics. So there is the general kinematics. So there are the velocity of the particles, and then there is the other layer of kinematics that is in the internal degrees of, I don't like to call them internal degrees of freedom, in the other degrees of freedom, the microscopic, let's call them microscopic degrees of freedom of the material, which, for example, in that case is the orientation angle, the mean orientation angle. We kept in that case the variance constant, just for simplicity, so we had only one parameter, not two. So we had one remodeling parameter. So practically we imposed then not only the virtual work of the regular forces, but also the remodeling forces. And those forces are the dual of the velocities of the remodeling parameter. So that would be the time derivative of the angle. So how the angle changes in time. So in that case, this is not very biological, it's very mechanical. And it doesn't render justice to the cells yet.
But there's some rule for how the orientation angle should change.
Yes.
Where I guess you're starting from some happy state.
Yeah. We can start. We actually started from. We started from random. We just imposed top and bottom. Top and left, right, top, bottom. It's all the same. So top boundary condition, bottom boundary condition, and then random in the middle, and then the material evolved that way. That's what happened. It's similar to what has been done classically for bone remodeling. You know, they give the trabecule a random arrangement, and then the trabecule actually orient with the principal stresses, and then they do the Wolff's law practically.
So in fact, your cells are causing that random structure first, and they are only there to maintain that random health system. Would that be correct?
I see it, the way I see it is that if you look at the evolution from the fetal state to the mature state, at the beginning it's all cartilage, all the bones are all cartilage, and they're all possibly, everything is random, and then things evolve so that the random orientation doesn't work anymore, and it has to be, depending on the load. Now we applied the compression, in fact, to simulate what happens in a real joint. So depending on the load, then they have to reorient in a certain way.
But if you have osteoarthritis, the cells must have an activity.
Yes. Yes. And what happens in the case of osteoarthritis is there is a mechanical disruption of the fibers too, right? So it's not just, it is both mechanical and is biological. So no, there is a biochemical.
So you must replace it.
Replace
the damage.
That would be fantastic. I don't know how to do it.
Or maybe the cells know.
Maybe the cells know, and the idea would be by looking at some point into what the cells are doing and what the cells and how the cells respond, to tell the cells, please, would you mind?
So do you think that the cells are mechanically controlled for their function?
I think they're both mechanical and chemically controlled, because the cells do sense the mechanical stimuli. They sense strain, they sense stress, and they respond to that. I don't understand absolutely anything of cells, but
so it's about time.
Hmm?
It's about time.
Did I understand? Yeah, I guess, yes, probably. Yes. Right.
When I hear you talk about the probability distribution of the fiber
Yes.
orientation,
Yes.
I feel like I should be seeing a distribution function or a probabilistic representation of the permeability. But
Yes.
I don't. It's just
It's
it's points on the graph.
it's after I integrate, but I have to do an integral. So what I do, I will write some blasphemy here on the board. I used to like when we had the board over there, it was nice. Now I have to, sorry, you mind? So, I'm not trying to emulate Professor Jaguint, I just don't have any other choice. So what happens is I have my permeability of the ref that I find with the boundary value problem. I solve it. There is a procedure to find that, and that's a function of the direction. Then what I do is, okay, I'll take an integral over all possible directions. That's not a dollar, it's a sphere. It's a second order sphere. And I have a probability fibers. So that is my permeability. So the permeability I plotted is this one. It's not this one. Because overall, what I see overall, if I sit on a fiber, I see this one. But that's just relative to what I would see in one fiber. But in a small enough, so that's my referential element of volume. Then I take a bigger referential element of volume. I have a lot of fibers in many different directions. Then I see the average.
Does the distribution function change with the disease states?
It does. It does. In fact, it gets disrupted a lot in the superficial zone, particularly in the superficial zone. And if you see, I forgot to bring, to put a couple, but if you see micrographs of histological sections of cartilage, healthy and osteoarthritic, you see that in the healthy one it's nice and smooth and beautiful. In the healthy one, in the osteoarthritic one, you see it's all, so the superficial zone doesn't exist anymore. Yes.
So if you look at cartilage in a very young animal, there's not as much matrix and there's more, the cell density is higher than an adult.
Yes.
And so as you use your cartilage and you grow, you're laying down matrix. And so I guess the question is the randomness intrinsic to the tissue? Or is some of that randomness actually not random at all, but really in response to the loading pattern?
Some of the randomness is there because of the loading pattern. In fact, apparently, in the middle zone, the orientation has to be random to respond to, well, it has to be random for two reasons. One, there has to be some sort of smooth transition between being oriented this way and being oriented this way. Nature doesn't like anything abrupt, right? So in that transition, the fibers are all orienting themselves in a different way, and they're doing on different planes, and that's why overall we see noise. We see white noise, and so we say that the orientation is random. So part of that is because we have to pass from this boundary condition to this boundary condition, and part of that is probably because that's the best way for the tissue to work.
Okay, so but we know that cartilage is heterogeneous, and where you load it or unload it or protected by the meniscus or whatever. So is there heterogeneity in the quote-unquote randomness depending on where you actually look at it?
So can you do that? Tell me that again?
Is the randomness uniform throughout the cartilage, or is the random nature of what you measure dependent on the location within the cartilage of the joint?
Is there structure?
I don't know how much it varies. I would have to look into it to see in different regions of, say, a femoral groove, in which the loading is very different, of course, depending on the region. Whether the zones, for example, are, because the zones are easily identifiable by looking at histological sections and looking at the cells. So I don't know. I would have to look into that.
How could you look at the anisotropy of the randomness? How could you look? What measure would you have practically to monitor that anisotropy of randomness? That will be coming from the integral, and depending on the probability distribution, I get a different anisotropy. So for permeability, I only have two choices. Well, three. It can only be isotropic, transverse isotropic, or orthotropic, because it's a second order tensor. For elasticity, of course, is a lot more complicated. There are all the crystal structures that I can see from
triclinic to isotropic. Of course, I can see everything. But for a second order, I see, for example, if the probability is, okay, if you look at this one is by definition transversal isotropic because I have one fiber and isotropic matrix around. So the axis of transversal isotropy is the axis of the fiber. When I integrate, then it depends on the symmetry of this one. So if this is transversal isotropic with respect to another direction, now let's say that I have this direction, symmetry direction for the probability, and then I have my rev is here, then I integrate all the revs. Overall, I get transversal isotropy. If this does not have symmetry, then I will not get symmetry. I will get orthotropic. For a second order tensor, no symmetry means orthotropy. So it all depends on the symmetry of the probability. In fact, it is not true that the probability is always transversal isotropic. In the superficial zone, in fact, Mosen is modeling it orthotropic.
Stop.
With the double minimum energy functional, would it be possible to look at the effect of curvature on how that distribution? Well,
curvature or what?
The curvature of the top and bottom surfaces. You probably did 1D case for the example, but I'm thinking along the lines of, rabbit have a very different distribution of the fibers versus humans and larger animals. And if that sort of simple minimization of the energy functional could explain that, that'd be really neat. If you studied like curvature, that would be typical of rabbit versus curvature of a human.
That should be something to look at.
Yeah, it'd be very simple.
Yeah, no, that'd be fantastic.
It'd be neat.
Let's.
Oh, and also along the same lines, have you thought about imposing a mechanical boundary condition as opposed to an orientation of the fiber in that model, rather than say, okay, fibers have to be vertical on the bottom and horizontal on the top? Maybe fibers have to be fixed in all translation degrees of freedom in the bottom and fixed in only vertical displacement on the top. And if you got the same results, that'd be really neat too.
But why would I impose vertical? Why would I impose the displacement condition rather than an orientation condition?
I feel like you have to put something up there to make it go to that alignment.
But it's not that I have migration of fibers, right? It's not that the fibers move.
Yeah.
They may.
Like the thickness couldn't change, but maybe it could. I don't know. I think it just would be a nice interpretation if it works, because why do the fibers have to be vertical on the bottom, and why do they have to be vertical on the top? Like in the bottom, they have to be attached to the bone. That's a mechanical constraint, really. In the top, why do they have to be horizontal? Especially in the top. Why in the top? Horizontal.
In the top, horizontal, because that's the way in which the joint slides. So that's also, I see it also as a mechanical reason. So I want to have that resistance to the sliding. No? At least if I were God.
Just thinking of things you could do with that weird double minimum energy.
Mm-hmm.
I'm just thinking of things you could possibly do. Cute little studies for the double energy minimum.
So using the double energy minimum
right?
on some other parameter, you mean?
Yeah. That might be a little more meaningful than just saying it's got to be vertical, it's got to be horizontal. What's the reason for that?
Let's talk about it tonight.
I don't understand quantum mechanics at all. So.
We can, no, it's something I would like to talk about more. Yeah, sure. Thanks. Thank you.
Yeah, great talk. I don't know much about the mechanics of biomaterial, but at the end of your talk, like you're talking about possibilities for the clinical application. So can you predict some progression of the disease, such as OA or?
One thing that I mentioned was the question whether I can predict if osteoarthritis is coming or not. Well, if the person breaks a ligament, probably it's not kidding. That we know. But from hopefully one thing that will work, and it will surely not work next year or in 2 years. But with I have big hopes for the diffusivity, because the diffusivity can be studied non-invasively. So if you can link permeability, because permeability is known to change a lot, it doubles in an osteoarthritic subject. It doubles or more. So I'm hoping that if there is, in fact, this connection, this mechanical, geometrical, chemical connection between permeability and diffusivity, then measuring diffusivity is relatively easy. Permeability, you have to take off the joint, and the person may not be happy. But diffusivity is non-invasive; it can be done. So that would be the first thing that actually could be used almost right away, not quite right away, but it could be an indicator.
There's some evidence that on top of the superficial zone is the lamina splendens.
Yes.
Which actually seems to control permeability. So if you disrupt that very, very, very top layer, which is very, very thin, the permeability is altered dramatically.
Of course. Well, that would be yes. What would change would be the overall permeability. So the bulk permeability would change, because I'm practically playing with the boundary condition that I have. So how much fluid can it get from the surface? Yes. Yeah. So
it depends on the deformation, that how much you're going to lose each time. So the loading, the extent of the loading is actually going to end up affecting permeability and loss of the whole tissue over time. So a single event might not change it dramatically, but continuous loading is going to end up depleting it.
Depleting. Yeah. Well, you mean depleting the lamina splendens completely?
Well, it's going to end up depleting the functionality of the compression to resist.
Yeah, because the tissue would not be able to retain the fluid anymore. Yeah, right.
Me? Thinking about the fluid on the surface of the tissue, would it be one of the boundary conditions that the fluid can only, or would most likely go against the surface? So that would affect the orientation of the particles. While at the subchondral bone, it will have to be against.
I don't know if we can say that the fibers have to be that way because the fluid has to go tangent. I'm not sure if it.
Mechanical.
But this is a discussion we should have for your next trip to Torino, maybe.
One thing I don't think I understand about fiber orientation with disease, and I don't know how this plays out in the remodeling algorithm, but if you go from horizontal to random to otherwise vertically aligned, and it's anchored in the bone, and then but what I understand with OA is that you get a marching of the tide mark, and so the calcified cartilage, subchondral bone replaces calcified cartilage with more subchondral bone. Calcified cartilage replaces more articular cartilage with calcified cartilage. And so you would think then that.
But that would be in late osteoarthritis. In early osteoarthritis, what you have is an erosion at the beginning. You also get the erosion of the tissue.
I think that might be
So
debatable.
they go.
But for sure, in late stage OA, you get sort of the calcified cartilage has replaced the articular cartilage. So what then does that do to the fiber orientation? Does that mean that as the calcified cartilage takes over the articular cartilage, that the ones in the middle zone that were randomized become more vertically oriented?
I don't know. What I know is that there is really no orientation in the superficial zone. It starts to be random in the superficial zone. I know that for sure. I don't remember which reference to give you right away. I would have to look up a couple of references, but I know it's like that.
But it's always vertical, even in the end-stage disease state, you always see it vertical in the deep zone.
Yes, as far as I know, yes.
Just to make a comment, there will be a debate in the meeting of osteoarthritis Orthopedic Research Society next year in New Orleans. It's exactly the same topic. Which one comes first? Is it cartilage or is it the subcomponent? So make sure you go there and then listen to it. But Salvatore, I have a question for you.
Oh God.
So, so in your remodeling models, you managed to predict from the healthy cartilage to OA cartilage, the quadrifiber orientations. But if I want to do the remodeling from the very start, say from immature cartilage to mature cartilage. So as far as I know, immature cartilage doesn't have specific orientations of the collagen fibers. They're all randomized. So how, I'm not sure if you have done it or if you know anybody has done it.
Something like what we have done.
Like
like what we have done.
How do you make, since you always say that the orientation is mechanically driven, like how the collagen fibers is oriented is mechanically. Can your model or someone else's model do that remodeling from the immature cartilage where you have no orientation for the collagen fibers, they're all randomized, to the healthy cartilage collagen fiber orientations?
I think this model could do that on a, it's a matter of time scales too. So we would have to set, probably would have to set multiple time scales for, and it would be probably more complicated than this, but it's probably something to look into. Yeah.
They'll be very good for
very
understanding of how the disease progressions from the very, very early osteoarthritis to end.
Yeah, because it's
then you
somewhat is the inverse process. Is the inverse process? Yeah, exactly. Yeah. It's somewhat the inverse process. Yeah.
Venus and then Scott.
So, Salvatore, in that Nature paper, the permeability and that, oh my God, curve, is it it's experimental results? So how were
they had a microtome. So what they did, and they couldn't do it very well the first time. So the first time that they did the experiment, there is a paper in the same year or the year before, or 2 years before, I don't remember. The first time they did the experiment, so if this is my favorite coordinate, I call it C. That's a bad C because let's do a better C. That's a better C, okay. So that's the vertical coordinate. That will be 1, that will be 0. 0 for me is the time mark and 1 is the surface. Everybody else does 0 here and 1 here. I don't care. So they found, the first time they found this. Oh, then it's true, they said, but problem. They actually found this. They had no points in the superficial zone because they couldn't cut very well. So they used a better microtome. They cut to the superficial zone. They measured two really thin slices, and they practically measure they slice the tissue, and they measure the permeability in each slide. So the variation within the slice, they go consider it homogeneous within the slice. And so they.
Permeability change when you cut it when as opposed to when it's all the zones are still intact?
Whatever you measure, you are influencing, right? It's like the Schrödinger cat. No, you open the door to check if the cat is alive, the cat dies. So you know the cat is dead. Of course, it's like a Gilak's experiment for the cell. No, he takes this cylindrical sample, cuts it into, puts a glass, does the compression so he sees the cells. Is it damaging the cartilage? Yes, of course. There's nothing better than that. What can we do? So probably it does affect somehow, but it affects, likely it affects all layers more or less in the same way. Right? So if all layers are affected more or less in the same way, but still you see, though the significant part is that you see this maximum here, and then it drops again. So the fibers have got to do something with that, because it's precisely because of the orientation of the fibers here. No, the fluid is impeded in this direction.
So did anyone did it while the whole cartilage is still there?
But then you get a bulk value.
Yes.
Oh, yeah, sure. Everybody does it. It's very easy.
So okay, but did you see something like that?
No, you can't. You can't. You just see the average.
Because you have.
See the image. So that's why you have to slice. There's no other way, really. Unless we can find anything fancy with your microscopy magic tools. I don't know.
I know you said you don't like to think about the cells, but
No, I don't say I don't like to think about cells. I'm ignorant. It's different.
an issue that I always have
Yes.
is how do we go about dealing with the cellular processes, even how they affect the mechanics of the cells. So we'll see stuff experimentally, like when we load the cartilage under like stress relaxation, say, and hold it there and image the cells, they lose their volume as we'd expect. But if we load it cyclically, the cells maintain their volume under cyclic loading. And it's like, mechanically, it doesn't explain this at all. So in my mind, I've always said that must be some biological process that the
True,
cells
but
switches on.
what are the time scales? So they lose the volume after
I think
compression
like
for how many
20 minutes of
seconds?
cyclic loading, they don't lose volume. They maintain.
But
level.
probably there is no time for them to lose volume. Because it's cyclic loading with what frequency? What is the frequency?
I think 2 hertz. I don't remember exactly.
But probably they don't have the time. No, if you do a compression test and you leave it there for 10 minutes, they will lose water. But if you do this, probably there is no time for them to lose water.
Okay.
Probably.
Okay.
Probably.
Well, I guess the question.
That's my mechanicistic
the
explanation as a.
So a cell can close and open aquapores in
Yes.
the membrane, right?
Yes.
And that's like an instantaneous. I go from a porous material to an impermeable material. Do you see us ever reconciling that in continuum mechanics, where we need smooth, differentiable things?
Oh, of course no.
No. So is there no hope?
No.
To capturing.
Well, even fraction mechanics doesn't comply with continuum mechanics because you have a point that splits in two. No? But of course there are ways to go around it.
Are you the person?
So it's a non-standard. It would be a non-standard theory or something like that.
Are you the person to think about this sort of thing? Or?
Never. I've never. I think again, Vincent is right. I should probably look into the cells more. Well, 75 papers.
It would be nice, like, to start to get at that stuff. I think. It seems very difficult in my mind.
But no, it can be because it can be like a localized source or like a localized flux on a surface, right? It could be something that can be looked at like that. As I said, also fraction mechanics, according to the standards of continuum mechanics, fraction mechanics doesn't exist, but in fact it exists, and in fact it is studied. So it can be one can probably go around it.
I guess this is more of a follow-up to Scott. Have you tried modeling the cell as like a poroelastic material?
Yes.
Yeah, and it didn't match what you see experimentally? Because I would think that if you set the permeability right, you could get something where it would need time
I do math.
for that fluid to flow out and allow its volume to decrease.
Yep.
And if you loaded it cyclically, there wouldn't be enough time for that to happen. So I think you could capture that behavior that way. But.
Yeah. It's strange because the cells recover slower than they deform, right?
Mm-hmm.
Fluid flows back in slower than it flows out. So, and I think we should still see a loss.
It's probably ratchet, a type of ratchet process too, that in one way works in a certain way and the other way works differently for many possible reasons.
All right, any other questions for Salvatore? Before I end this, I have to ask this question as a single reporter.
Or not.
Why do you choose articular cartilage in the first place instead of skeletal muscle?
Because I looked at the papers and I saw stresses and strains, and I said, let's go with cartilage. That's simple as that, really. Because Butter sent me both papers on muscles and papers by Jung Woo on cartilage, and I said, no, this one.
And you never crossed your mind that you want to work on skeletal muscle?
It has crossed my mind, and I never did, and that was a mistake. I would have liked to do something, but it's too late. No, because now I barely have the time to supervise my students, and doing my own work is already science fiction. I do it when I have time. I do it when I can.
So did you think that you did the
Well, from the Leibnizian point of view, if I were Leibniz, I would say yes, of course, because it's the one I made. It's the best possible decision because it's the only one I made. So I have no choice at this point. I like Leibniz, by the way. Maybe I'm biased.
Right. Thanks. Okay, there will be no seminar until January 11th next year. But please join us back next year and with more exciting seminars in stores. You can check the schedule on our website for next year's schedules. So until then, I wish you a merry festive season and I will see you next year. Bye-bye.